Here we'll review Newton's first and second laws, and then we'll talk about the force of friction. Alright, so we've got a block with a weight of 4 newtons. It's suspended from the ceiling by a piece of string. What is the magnitude of the tension in the string? Well, here's our free body diagram of the block. We have the weight, which is 4.0 newtons downward. And we have force of tension, which acts upward. The block is suspended from the ceiling and it's not moving. And so if it's not moving, that means that its acceleration is 0. If its acceleration is 0, Newton's second law tells us that the net force acting on the block must also be 0. So if the net force is equal to 0 for the block, that means that the magnitude of the force of tension has to be the same as the magnitude of the force of gravity or the weight. So, a 5 kilogram object has an applied force of 30 newtons acting on it. What is the magnitude of the acceleration of the object? Well, here we can use the formula for Newton's second law. Acceleration is equal to net force divided by mass. And we know the mass of the object. The difficulty here is that we don't know the net force acting on the object. We only know the applied force acting on the object. So we know the applied force, but we need to know the net force. So in this case, we cannot determine the acceleration of the object. There may be other forces acting on the object, and we have not been told what they are, if there are any. So, frictional force. There are a number of different kinds of frictional forces. We're going to focus on 2 types of sliding friction, for the most part. There's also rolling friction, which we'll probably talk about a little bit, but not very much. We should first review the concept of weight, because weight can affect friction, sliding friction, to be sure. So recall that the gravitational force acting on an object exerted by a planet or a planetoid, moon, etc., is also called the weight of the object. And we can calculate the magnitude of an object's weight using this formula. Fg is equal to the mass of the object in kilograms times g, the acceleration due to gravity in meters per second squared. And on Earth, that acceleration looks like this, 9.8 meters per second squared. Weight is therefore measured in newtons because it is a force. The normal force, as you may recall, is the force that acts to keep objects apart. So this is a contact force. So an object sitting on the floor would have a normal force exerted on it by the floor, perpendicular to that surface, perpendicular to the floor. So for the object on a horizontal surface with no vertical applied force, the normal force would be equal to the weight, because there's no acceleration in the y direction, so the forces in the y or vertical direction must be balanced. So in this case, this would be a good free body diagram for a box being pushed rightward across the table. You'll notice that the magnitude of the applied force is shown to be larger than the magnitude of the friction force, which means that the object will have a net force to the right in this case, and will be accelerating to the right. So the net force in the vertical direction is 0, which tells us that the forces have to be balanced in the y direction. But if there is a vertical applied force, then the normal force will not be equal to the weight in magnitude. Here's an example. A 5 kilogram book is resting on a table. If Ms. Roseberry is pushing down on the book with a force of 20 newtons, what is the normal force the table is exerting on the book? Well, let's look at our free body diagram. Here we've got the normal force, the magnitude of which is unknown. We have our applied force, which is 20 newtons downward, and we can calculate the weight of the book, which we find to be 50 newtons, also downward. Now the book is at rest, and so there is zero net force in the y direction. So the normal force, which we take to be positive, plus the force of gravity or weight, plus the applied force must be equal to 0. So you'll notice here that because the weight is downward, the weight is negative, and the applied force is also negative because it's also downward. So when we rearrange our equation, we get a normal force with a magnitude of 70 newtons, and we already know that the normal force is upward from our free body diagram. Now the normal force is always perpendicular to the surface. In fact, that's what normal means. We don't call it the normal force because it's not weird. We call it the normal force because normal means perpendicular to something. There's the symbol for perpendicular. So if the surface is vertical, then the normal force would be horizontal. Now friction, as we mentioned earlier, is the force that acts to oppose any motion of an object or any attempted motion of an object. So it's always opposite in direction to the attempted motion or the motion if the object is moving. The size or the magnitude of the force of friction will depend on a couple of things. It depends on the magnitude of the normal force acting between the objects or the surfaces in contact, and it also depends on the properties of the surfaces in contact. So what kinds of materials are in contact? The way that we describe those properties is using a factor called the coefficient of friction. We use the Greek letter mu to denote coefficient of friction. Mu, incidentally, was my cat's favorite coefficient. My cat seemed obsessed with coefficient of friction. Never stopped talking about it. So mu is the coefficient of friction, which is determined by the nature or the properties of those surfaces in contact with each other. Mu is one of those rare quantities in physics that has no units. Most of the measurements or quantities that we measure in physics have units, but mu is a unitless ratio. A really high coefficient of friction is going to be around 1, or a little bit less than 1. Many of them are significantly lower than that, though. Here's an example, wood on steel. Now you'll notice there are two different types of friction coefficient. We have the kinetic coefficient and we have the static coefficient. You'll also notice that the static coefficient of friction is greater than the kinetic coefficient of friction. That is always the case. It's more difficult to get things moving than it is to keep them moving. If you think about Newton's first law, that will make sense to you because, of course, objects at rest tend to remain at rest, and objects in motion tend to remain in motion with a constant speed in a straight line. For steel on ice, we see again coefficient of static friction is greater than coefficient of kinetic friction. So the coefficient of kinetic friction is the coefficient for surfaces that are sliding relative to each other, and the coefficient of static friction is for surfaces that are not yet sliding. They are still at rest. For rubber on dry concrete, we would expect these values to be significantly higher, and they are. So 1.1 for coefficient of static friction, 1.0 for coefficient of kinetic friction. And we would expect those coefficients to be high because we use rubber in our car tires and we want them to have a lot of friction with the road to keep us safe. Alright, let's look at an example. A 1,200 kilogram car without ABS brakes is skidding on dry concrete. So with no ABS brakes, that means that the brakes can lock up, which means that the wheels can lock so that they will not turn at all. So the car will just skid along the concrete. What is the magnitude of the force of friction acting on the... Well, here we have our given values and our unknown. Coefficient of kinetic friction in this case, 1.0. And now we'll select our equation and solve. So the force of friction is equal to the coefficient of friction times the magnitude of the normal force, and then we'll substitute the values in. Normal force, of course, in magnitude in this case can be found using mg, because if there's no acceleration in the vertical direction, the forces must be balanced. In that case, the normal force has to be equal in magnitude to the force of gravity. As we saw earlier, that's not always the case, but it is the case here. Alright, a little bit more practice. A crate has a mass of 20 kilograms and it's being pushed with a constant velocity across the floor with a horizontal force of 63 newtons. Find the coefficient of kinetic friction between the crate and the floor. Well, if there's no net force acting on the crate, the force of friction must be equal in magnitude to the horizontal applied force. So the magnitude of the friction force has to be 63 newtons, and it has to be opposite to the direction of motion. The normal force has to be equal in magnitude to the vertical gravitational force, again because there's no acceleration in the vertical direction. So if there's no acceleration in the vertical direction, then the net force in the y direction has to be 0. And so normal force has to be equal in magnitude to the force of gravity acting on the object. So now we can divide our frictional force by the normal force to get the coefficient of friction. So in this case we get 0.3, and once again you'll notice there are no units because coefficient of friction is a unitless ratio. Alright, we'll try some practice together and we'll see how we do.